The Zoom session is being brought to you by the Fractal Almond Octave Z forming. Let's see about this. Excuse me. Okay, why is it like that? Okay, I see. Excuse me. Okay, today we'll be doing section 8.3 and 8.4. 8.3 is about geometric sequences, and 8.4, a very useful one, is about the mathematics of finance. Okay, let's begin. Okay. Let's see, we're recording. Okay, so geometric sequence. It's the form A, AR, AR squared, AR cubed, and so on. It starts with A, the first term. Each time you multiply it by R, the common ratio. And as you go on in steps, eventually you will reach A, the nth term will be A R to the n minus 1. Minus 1 and minus 1 because at a 1, that's AR to the 0, whatever. So, for example, AN is 2 times 3 to the n. The first, the common ratio is 3. The first 5 terms are 6, 18, 54, 162, and 486. Okay. A geometric series is a sum of a geometric sequence. So you go from AR to the n minus 1, sum them all, A plus AR plus AR squared, all the way up to AR to the n minus 1. All right, so it's the sum of a geometric sequence. Now, suppose you have Sn is equal to this, sum from A up to AR to the n minus 1. You multiply by R, it moves it over one step. A becomes AR becomes AR squared becomes AR cubed, and AR to the n minus 1 becomes AR to the n. Now, this series, this sum and this sum are almost the same in all the terms in the middle. They just differ from the first term here and the last term here. So here's what we do. We subtract Sn minus RSn, like that. Term A survives. All these middle terms cancel out. So AR to the n minus 1 survives in the minus. So Sn minus RSn equals A minus AR to the n. Okay, we factor out an Sn here, 1 minus RSn, factor out an A here, A times 1 minus R to the nth. So the nth geometric series to n terms is A times 1 minus R to the n over 1 minus R. This is the series. This is the formula for the series. So for example, here we have 1 plus 3 plus 9 all the way up to 2187, which is 8 terms. So, well, let me double check that. 3 to the 8, is that right? 6, 5, 6, 1. How about 3 to the 7th? Yeah, okay. This last term is 3 to the 7th. The first term is 3 to the 0, so there's 8 terms in all. So Sn will be 1, A1, that's A is equal to 1, over 1 minus R to the n over 1 minus R. So after a bit of arithmetic, you got 3,280 is the sum here. Here's a cute one. 1 minus 2 plus 4 minus 8 plus 16 minus 32, all the way to minus 2048. Let's see. 2 to the 11th. Yes. So it's 2 to the 11th here. Starting from 2 to the 0th here is 12 terms. And A1 is, and the initial term A is 1. The R, the common ratio, is a -2. That's why the negative, it's constantly flipping signs. 1, -2, -2 squared is +4, -2 third is -8, and so on. So what's the sum? Well, it's A times 1 minus R to the n over 1 minus R. 1 is 1 minus R is -2 to the 12th power over 1 minus -2. Comes out to -495 over 3, or -1365. All right. Now, if you have this geometric series goes on forever with no last term, that's an infinite geometric series. Now, there's some question as to what if that's even definable. There's a whole question of what's called convergence. These terms have to go to approach 0 for this to be really definable. But okay, so here's what we have: the limit as n approaches infinity of a partial sum, a times 1 minus r to the n over 1 minus r. Now here's the thing, the behavior of this depends upon the size of r. If its absolute value is greater than 1, then this r to the n keeps getting bigger and bigger and bigger, and the series diverges. It has no limit. If the absolute value of r is less than 1, then r to the nth approaches 0, and the whole thing, and so you get a times 1 minus 0 over 1 minus r. So the series converges to a over 1 minus r. So for example, 1 plus a third plus a ninth and so on forever is what? Initial term is 1 over 1 minus r, common ratio is 1/3. 1 over 1 minus a third, that's 1 over 2/3, is 3 halves. This sums to 3 halves. Or 1 minus a third plus a ninth minus a 27th and so on. Well, here the common ratio is a negative 1/3. And the initial term is 1. 1 over 1 minus ratio, negative a third. It's 1 over minus 4/3. 1 over 4/3 is 3/4. Now here's 1. 1 plus 3 halves plus 3 halves squared plus and so on forever. Thing is that this 3 halves is bigger than 1. So this is run away. It grows off indefinitely. And so therefore, this does not converge to a limit. It's divergent. Similar thing here. 3 plus 3 times 1.1 plus 3 times 1.1 squared and so on. This 1.1 is bigger than 1. So its powers diverge to infinity. So divergent. Here, however, 3 plus 3 times 0.09 plus 3 times 0.09 squared plus and so on forever. 0.9 is 0.9 is less than 1, absolute value less than 1. So we can this converges. It's a leading term 3 over 1 minus common ratio 0.9. That's 3 over 0.1 makes 30. This converges to 30. Now here we have repeating decimals as fractions. And the question is to write this as a fraction. 0.523 and the 23 repeats. 0.5, 23, 23, 23, 23, and so on forever. Now, we can break this into the non-repeating part, 0.5, plus the repeating part, 0.023, 23, 23, etc. Now, all right, we'll write this 0.5 as it stays at 0.5. Here, let's pull out a 0.023 factor, and there'll be that times 0.101010101. Now we have a repeating decimal visible as and therefore convergent series. Here's how we'll do this. 0.5 we keep, 0.025 we keep. This infinite series is 1 plus 1/100th plus 1/100th squared plus 1/100th cubed, etc. So we'll replace this by leading term a over 1 minus the common factor 0.01. So 0.5 plus 0.025 times 1 over 1 minus 0.01. So this is 5/10. This is 23 over 1,000. This is 1 over 0.99. Okay. Now, if we're going to write this as a fraction, we have to make sure to write this in fractional terms. 5/10 plus 23 over 100 plus 100 over 99. And now, okay, I could just, push this into a calculator and get back this fraction, which achieves nothing. We want to write it as a ratio of integers. Well, okay, 23 over 1,000 times 100 over 99. The hundreds cancel, left with 23 over 990. Then using basic fraction arithmetic, we get 259 over 495. Oddly enough. Okay. I suppose I cheated, and if I'm going here to here, I cheated in using the 2fraction app on this calculator. But okay, so there we are. Now let's stop for here.